Let's talk about how the two formulas for compound interest can be derived for secondary students. In this video, I will strictly use letters. When actually deriving this or explaining where this comes from for students, you probably would want to use numbers. However, we're all grown-ups, and so I'll simply use algebraic notation when doing the derivation. First off, let's assume we start off with $P at the start. We have an interest rate of R, and we're going to let this go for T years, where T is an integer. Then after 1 year, the interest would be equal to P times R, and so the total amount would be equal to the original P plus P times R, which works out to be P times 1 plus R. So that's after 1 year. If we now go to a second year, the interest will be the amount after 1 year is P times 1 plus R, so the amount that we have after 1 year times the interest rate R, just like before. The amount that you have times the interest rate. And so the total after 2 years would be equal to the amount that you had after 1 year, which is this part, plus the new part that we just calculated, and so this simplifies. I can factor out the P times 1 plus R, and what's left will be 1 from the first term and R from the second term, which gives P times 1 plus R squared. And by now, hopefully students can probably guess what happens at T years. The total would be equal to P times 1 plus R to the tth power. R is the rate at which it accrues interest for 1 year, and T is the number of times that it compounds. Okay, now the next generalization is, suppose that we compound the interest n times a year. Okay, so the unit of length, or unit of time, would be equal to 1 over n years. So if you compound it twice a year, then we worry about a half year. If we compound it 10 times a year, we worry about a tenth of a year. So the rate for each time that it accumulates, rate for each unit, is going to be equal to the total rate per year, this divided by the amount of time it takes, R over N. And the total number of units would be equal to the number of years times the number of times it's compounded per year. So before, the interest rate was R for 1 year, and I compounded it for T years. Now I'm compounding where the rate is R over N, because I'm compounding interest multiple times per year, and therefore there's going to be multiple blocks where the interest gets compounded. And so that gives us the familiar formula, P is equal, A is equal to P times 1 plus R over N to the N times T. And so there is the formula for discrete compound interest. As I said, we probably would use numbers for this. We were going to do that in class, a derivation using numbers as opposed to just simply letters. That would be probably more clear for the first explanation, the first introduction to this concept, but even using numbers, the theory behind the numbers is what you see on the screen right now. So that's the formula for continuous compound interest. Let's now talk about the formula for continuous compound interest. And the idea is, how do you start from the formula for continuous compound interest, or for discrete compound interest, pardon me, and end up with the formula for continuous compound interest. So the way we're going to do this, we'll do this in cases. First off, case 1. Let's make a very simple assumption that R is equal to 100%. Then the formula reduces to A is equal to P times 1 plus 1 over N to the NT. And let's write that as P times 1 plus 1 over N to the N, and then that part gets raised to the Tth power. Now let's investigate what happens to the part in brackets as n gets large. So we're going from something that goes yearly to monthly to daily to hourly to every second to continuously. So what happens to the thing in brackets as n gets large? Well, this can be investigated with a calculator fairly simply. So let's just take 1 plus 1 over 2 raised to the second. That's something. Now let's just let the value of n increase. 1 plus 1 over 10, let's make it 12 for months, 1 over 12 to the 12th power. That's larger, but not tremendously larger. If we do it every day, 365, raised to 365, we get 2.714. If I were to increase this to, say, 1 over 100,000, raised to the 100,000, we get 2.718268. So this is increasing, and you probably have done some problems to convince yourself that as the frequency of compounding increases, the amount increases, but it's increasing, but it's certainly leveling off. And the number, of course, that it is leveling off to is E, 2.71828. So this can be, you can do some numerics with this to convince students that the part in brackets increases but levels off to some number, and that number is simply given the name E. So this goes to P times e to the t, because the thing in brackets goes to E. Now, that's not a formal proof. We did not prove that the thing in brackets goes to as that number E. We also did not prove that the function x to the t is continuous, so that this limit occurs if 1 plus 1 over n to the n goes to E. However, this certainly seems reasonable, and so that's our explanation for the case r equals 1. Okay, now for the general case, we have P is equal to, A is equal to P times 1 plus R over N to the N times T. And now the way that we're going to approach this is that we're going to force the inside here to look like the inside over here, where there's a 1 in the numerator. Here there isn't a 1 in the numerator, so the way that we're going to get a 1 in the numerator is by letting n be equal to m times r, so that m is equal to n divided by r. then this expression can be written as P times 1 plus R over M times R, and N is equal to MRT. And so I now have P times 1 plus 1 over M to the M, all raised to the RT power. Now what happens to M? As N gets large, M also gets large. N divided by R gets large if N gets large. And so likewise, the thing in the brackets here also gets closer and closer to E as M gets closer to infinity. So this goes to P times e to the RT as either M or N goes to infinity. And so that is our justification for the general compound interest formula, P times e to the RT, based on the formula from discrete compound interest.